This is calculus of a single variable from the Larson book, and the big ideas from sections 3.1 to 3.3. First off, in section 3.1, we talked about using a secant to approximate the average rate of change over an interval. So if I have this curve, I want to find what is the slope at this point. I could get an approximate slope by drawing in the secant line and then calculating the slope between those 2 points, f of b minus f of a divided by b minus a, and that would give us the slope. However, that is just an average, and it's an approximation for the slope at that point. We can move point B closer to point A, we'll get our better approximation, and eventually we turn that into a limit to find the instantaneous rate of change. So if I want to figure out what is this exact slope that is going through that point, I don't want my B value to be very far away. In fact, I want it to be super close. So then we take the limit as delta x approaches 0. In other words, our change going from C to the next point to the right is going to be very small. So we have this other point, C plus delta x, f of C plus delta x. And we're going to calculate the slope between them as the distance between them approaches 0. So like the problem before, we are just going to calculate this slope, change in y over change in x. And then these c's are going to cancel out. They're going to eliminate each other. So there is our formula for the limit, which becomes our formal definition for the derivative then. If we want to find the derivative at a point, we can use the alternate form. So for example, we have h of x equals this, and we want to figure out what is the derivative at c equals -1. We could say h prime of x, our derivative, is the limit as c approaches -1 of 2x squared minus 3x minus, and if we plug -1 in, 2 times -1 squared is 2, -3 times -1 is 3, so we have -5. It's going to be over c minus -1, makes it become c plus 1. Now, if I plug in -1, we get 0 in the numerator, 0 in the denominator. That limit would be undefined. However, and try to simplify this. The denominator is now just c plus 1. The numerator, I believe, is going to factor about, should be x down here, x plus 1, 2x minus 5, and that will give us the correct factored form. And now we can simplify by dividing numerator and denominator by the same thing, plug in -1, and we get that this limit is -7. So the derivative at -1 is equal to -7. One more big idea from section 3.1, find the value of a to make f continuous, and once we've made it continuous, is it differentiable? Because not every continuous function is in fact differentiable. If we want this to be continuous, the two different sides of this piecewise function are going to have to link up with each other. So coming at it from the left, if we plug 2 in for x, and f of x as x approaches 2 from the left would be 4 plus 10 or 14, which means we want this ax plus 6 from the right to be equal to 14 also. We'll plug 2 in for x. So 2a plus 6 equals 14, which means 2a equals 8, or a equals 4. In other words, if a equals 4, these two different branches of the graph are going to link up with each other. Now it's continuous. On the other side of this, maybe it's differentiable, maybe it's not. What we need to do now is find the limit, or the derivative, from both sides using our definition of the limit. So the limit as x approaches 2 from the left of x squared plus 5x minus, we're going to plug 2 in, that's going to be minus 14, and it's all over x minus 2. This is our alternate form of the derivative, and if we evaluate this, we get a limit of 9. Now the limit as x approaches 2 from the right, now we're going to use the bottom one, 4x plus 6 minus 14, so it is coming from the right, this function minus f of 2 all over x minus 2. If we evaluate that one, we get 4. So what's happening here is, from the left side, we have a derivative or a slope of 9. From the right, we have a slope or derivative of 4, which means there is a sharp point, so it is not differentiable. Okay, moving on to section 3.2, we have these basic differentiation techniques. First one is the power rule. F of x equals this, then f prime of x equals 9x squared plus 10x plus 6, and then the derivative of a constant is 0. The next one, maybe we want to rewrite this as 6x to the negative 2 minus 7x to the 1/2 plus 3 times x to the negative 7/3. It's in the denominator, that's why it's negative. It's 7 over 3 for our exponent. So now if I find the derivative, y prime is negative 12x to the negative 3, negative 7/2 x to the negative 1/2, minus 7x to the negative 10/3, multiplying the exponent by the coefficient out front. This will lead into negative 12 over x cubed minus 7 over 2 square root of x minus 7 over x to the 10/3, or the cube root of x to the 10th. Although this green answer is fine, simplifying it to the black might work well for a multiple choice. Otherwise, it's just an opportunity to make a mistake. The next one here we have is h of t, and the square root of 7 doesn't mean that t is to the 1/2. This is just a constant number. So as we find this derivative, it's going to be square root of 7 using the power rule. Pi square root of 13. This is just a number. There's no variable in there. We're finding the derivative with respect to t, so that's 0. Likewise, this has an e on it, but it's not an e with a variable, so this is just a number. The derivative of this is also going to be 0, so there is our full derivative. Also in this section, we looked at the derivative of sine and cosine. The derivative of sine of x is equal to the cosine of x, and the derivative of cosine x is equal to negative sine of x. As far as exponentials go, the derivative of e with respect to r is going to be simply e to the r. And then lastly, we looked at rate of change, and this is one of the really big topics in this one. If we want to find the average velocity over a certain time, we're going to take the total distance divided by the total time. Of average, with calculus, we can get into instantaneous position, velocity, and acceleration. So our position function, s of t, is equal to some function. And the label on that is going to be in meters or feet or some other kind of distance. Let's just call it meters. We have some function, s of t, in meters. Now, if we want to find the instantaneous velocity, we divide that by the time, or we take the derivative of that, so s prime of t is equal to the velocity of t, and its label then would be in meters divided by the time, or seconds, because we're finding the derivative with respect to time. If we take the derivative of the velocity, so v prime of t is equal to our acceleration, that would be in a label of meters per second, or meters per second squared. Into the product rule, the derivative of the product of two functions is the derivative of one times the function of the other plus the function of the first times the derivative of the second. As an example, if we're trying to find the derivative of this one, we're going to take the derivative of our first function, which would be 6x times the cosine of x plus 2x plus 3x squared plus 5, the first function, times the derivative of the second. And we can leave it like that, or we can multiply it out, 6x cosine of x plus 12x squared minus 3x squared times the sine of x plus 6x squared minus 5 sine of x plus 10. Quotient rule, for this one we use the low d high minus high d low all over low squared. Nice little rhyme for us. In other words, it is low times the derivative of the high minus the high times the derivative of the low all over the low squared. As an example, the derivative of h of x is the low times the derivative of the high, 10x plus 3 minus the high times the derivative of the low, all over low squared. And with using the quotient rule, we can find the derivative of these other lesser important trig functions. The derivative of the tangent of x is secant squared of x. The derivative of cotangent x is negative cosecant squared x. The derivative of secant x is equal to sec x times tangent x. And the derivative of cosecant x is equal to negative cosecant x times cotangent x. And the last topic we'll look at is the function versus derivative graph. So we have this function of f. Our goal is to graph the derivative of that one. So I'll graph my derivative over here. One thing I notice is I plotted a few points on the x-axis. At A, the slope is going up, the derivative is positive, but at B, on the derivative, the slope is 0. At C, the slope is 0. And at D, it's going to be positive. So I can get an idea of what this is going to look like by plotting my zeros in there. And to the left of point B, it's increasing the entire time. When the x value is A, the slope is really big. Just to the left of B, the slope is really small. So what I see going on here is something like this. These represent all positive slopes. From B to C, the graph is going down, so the slope is negative. Then at C, it is back to 0. It's going positive again, and it keeps going more and more positive to the point where it's at D, where it's going to be very positive. I don't know for sure exactly how low it goes and some of these other little variations, but this is a decent idea of what this graph looks like. I see that this is a cubic, so it's a good idea that this is probably a parabola or quadratic, so maybe I can make it look more U-shaped, but this is getting those important points, these critical points where the slope is 0 onto the graph, and then thinking about the positive negative.